Okay, so here we have just we're going to talk about Gauss's law, so we're going to rush through electric flux and the definition of it, and then we'll get into Gauss's law. Here's an amoebic shaped object with our electric field going through it. And remember, we're somewhere in this electric field. And here's our particle, and it's going to fly off this way, right? And so this gives us an electric field strength of E. And remember that somewhere out in the universe we have an origin of our electric field, our positive charge, and this is going out to negative parts that are out somewhere else in the universe. Okay, so it doesn't really matter so long as we know that we start at positive and go to a negative part. Okay, but what is the cause of this flux? Remember, the lines begin at positive and go to negative. Okay, the crowdedness of the lines, so how packed they are together, is the strength of the field. Okay, and that the number of lines that we have is always proportional to our relative charge. Okay, so if we have double the charge over here and half the charge over here, then this is going to have twice as many lines coming from it as we have over here, that sort of thing. Well, if we take, okay, then we have our flux, where we have our all right, and these are spreading, these are going to spread out to to these negative charges out here. And if we have an area inside of this, all right, then our flux, oh, sorry, got to draw green. Okay, equals our electric field times the area that it's passing through. But that's just for one particular point, but if we have a varied surface, then equals the integral of E dot dA. Now, and our flex, and so if we have a volume here, so if we have a volume, right, and so here is a dA going that way, and 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 a dA going that way. But as we sum all of these, as we sum the field going through this area, if it's closed, then it's always going to equal 0. And the flux going in is negative, and the flux coming out is positive. And that's because of the direction of the area. So we have, this is going to have an area that way. It's going to be generally negative, and that one's going to be generally negative, and that's generally negative. So flux coming in, because the area is pointing against it, is negative flux, and the area flux coming out of it is positive. All right, well, let's draw a new object, or let's draw a bunch of charge here. Okay, and the field coming from this, we've got positive test charge, so all the field lines are going to be coming out like so. Okay, and then we draw an object. We have this charged thing inside of a closed object. So this is three-dimensional. All right, and here's this object that we happen to have. Okay, and along our object we have a dA. So there's a dA, and it's pointing this way, and our dA's always point to the outside of right? Well, if our area is always pointing to the outside of pointing away from the interior, and we surround a positive charge inside this surface, then all of our field lines are going to be pointing out, and all of our flux is pointing away, is pointing out, right? So we have a net positive flux anywhere around the surface of our object. Yeah? You guys follow me there? Okay. Well, because we have this flux, Okay, and flux is just the total number of lines, right? Yeah? Flux is just the total number of lines. Okay, it wouldn't matter. In fact, I don't want to call it number of lines anymore. I want to call it amount of lines. Okay, because it's a much more vague idea than number of lines. We can never really count a specific number of it. So what if we changed the shape of our object? So instead of this, we had something that was more like that. Okay, and maybe I could have done a brighter color aside from the green, but does that help at all? Not really. Okay, so we have one object, and then we change the shape of the object, but we still have the charge inside. Is that going to change the amount of flux that is leaving the object? No. All the amount of lines is going to be the same. The density might be different as we on any various place around the object, okay, but the flux does not change. Okay, so we've discovered that the flux, okay, it only depends on the charge in or on a shape. Okay, that's so that's our idea with flux here. So what we can do is create what's called a Gaussian surface, and so we put a charge here. All right, and we create a sphere around our charge. All right. Now, if we're here on the surface, okay, and I did not draw this charge in the center of the sphere. Imagine it's in the center of the sphere. Imagine, if you will. All right. This is dA. Okay, and our dA is in this direction, right? And so it's if it's a sphere, then our dA is going to be in the r hat direction, right? Yeah. If it's a perfect sphere, then our dA direction, the direction of that area, is going to be in the r hat direction, away from the surface. So, what is our if we have a charge there? Okay, the field around that spot is also going to be E equals KQ over R squared, also R hat, right? Okay, and that's going to be the same anywhere. That's going to be the same. If we come down here, here's our dA, and our E is going to equal KQ over R squared again, R hat, and no matter where we are on the surface of the sphere, they're always going to be in the same direction. Is that our dA and our field are always going to be in the same direction. Yeah? Okay. So our flux equals the integral of E dot dA. Okay, but our E is going to be constant since it's a sphere, and we're always the same radius away from the center. So we can take that out. Okay, and it's a closed surface. Okay, and so what is the dA? What is going to be our area for a closed surface if it's a sphere and it's a sphere, it's a perfect sphere? Okay, it's going to be A. And what's the area of a sphere? Oh, that's the volume. You're close. 4/3 pi r cubed is the volume. Take the derivative of it, and we get 4 pi squared, which is the. Okay, so the flux through the surface of a sphere is going to equal 4 pi squared E. Okay? Now, E, remember E is KQ over R squared. Right? Now, this all works because R hat and R hat, if we're dotting R hat and R hat, we get 1, right?
Yeah.
Okay, so, all right, so, we just got rid of the vectors because R hat and R hat is 1. Okay, equals KQ over R squared times 4 pi R squared equals 4 pi KQ EN. We put an EN here because this is enclosed. This is the amount of enclosed charge. Yeah? All right. Now, if you remember, K, I told you we'd be getting this today. K equals 1 over 4 pi epsilon naught, okay, which is the permittivity of free space. All right, so if we take this and plug that in here, okay, we're going to get phi equals the integral of E dot dA, okay, which equals Q enclosed over epsilon naught. 4 pi cancels with the 4 pi, okay, and that's what the K is, so Qn over, okay, and this is Gauss's law. That the flux for any particular enclosed surface, the total flux, is equal to the charge divided by the constant of permittivity. Okay, so that's Gauss's law.
So